Hello and welcome to our video lesson on pendulums. I don't have too much to talk about, but I at least want to talk about the characteristics that affect pendulums and talk about how to measure some features like the length, the period, and the acceleration due to gravity. These are all things that will affect our pendulums. So on this slide that I have right here, let me bring up my marker, it's called a Foucault pendulum. And I'll show you a video at the end of our slides, but this is a pretty cool pendulum. It's a very, very long string right here. Well, usually it's a cable. And what it does, if you've ever been to the Boston Museum of Science, is it is allowed to oscillate, but because the Earth is rotating, it actually affects the motion of this. So what will happen is that the mass will actually not oscillate in a straight line. It'll start to curve like this, and then it's really neat because we'll see it actually make a full circle. And I'll show you a video toward the end of the slides about this Foucault pendulum. But anyway, we're going to talk about pendulums. So just in general, some properties of pendulums, just some terminology if you're solving problems. They call this part the bob, if you look at it. And usually the string is some sort of massless thing, or it's on a very small cable. So the reason why we say it's massless, so that we don't have to use anything like the moment of inertia of the system. So if you hear that, just basically we're just looking and focusing on the bottom part here, which is called the bob. So one feature that is measured from a pendulum is called the amplitude. Very much like when we have a spring and we take that spring and we move it back from the equilibrium, that's the amplitude. The same idea here. So the equilibrium we're going to take from the normal of the ceiling basically, or where it's at its rest position. So this dotted line is the equilibrium position, if you will. And when I set that back, that is the amplitude. Now the best way to measure this change is through the angle, which is why any angle with a pendulum is called the amplitude. So this is the maximum displacement from this equilibrium position. So just like we've done earlier with the spring, the pendulum period is the same idea. If you start here, it's the time it takes to go over there and back. That's a period, and that's one full cycle measured in seconds. The other way, of course, is the opposite, is how many cycles did you make per time. So if you go back and forth like this, and it took that long, that's called your frequency. So that unit is hertz, and we've done these calculations before. And we have, but I could do this really quickly, just to do it for the sake of doing it. Here we go. So a pendulum makes this many vibrations in that many seconds. So for period, T is the time per cycles. So that will be the time to be 60 seconds divided by 36 cycles, like that. So 60 divided by 36 will be 1.67 seconds for the period. Now I could do this for the frequency, because now the frequency is the inverse of the period, so I'll do that because that's the easiest way to solve this. And when I take the inverse of that, I get 0.6 hertz. So you can use things like period and frequency to calculate features of your pendulum. Okay. So take a second to think about this, but which of the following characteristics changes the period of the pendulum? How big the mass is, the length, or the amplitude? So this is a good multiple choice question. So if you think about this for a moment, and then we'll come back to it. So let's do that. So something I'm just going to mention, although I'm not going to really focus on, is if you look at the free body diagram of the system, you can see that we have tension acting along the cable right here. And then, of course, as always, we have our force gravity acting down like this. But the interesting thing about the pendulum system is it's quite complex. So notice that we rotated the coordinate system to represent the net force, if you will, right here in the x direction. So with that said, we can actually write the restoring force as mg sine the angle if we use this rotated coordinate system. So when you do that, you have the tension here, you have the gravitational, and if you notice, this piece here is actually the same as this piece, so let's write that in. So this piece right here, and this is the hypotenuse right here, which is mg. So since this is opposite, this becomes a sine, and that's where this comes from, mg sine of the angle. So this is the restoring force. And as you might imagine, as I increase this angle, the larger the force. So just basically what this means is we meet the conditions for simple harmonic motion. So the easiest way to solve some of the pendulum features is to use energy. And just like we kind of analyzed with the conservation of energy, this is more of a reminder. At the very top right here, we'll have just potential energy. And we measure that potential energy from this line right here. So this h right here represents the height change from the bottom to the top, not this length right here or the length of the pendulum. So just be careful. This is a vertical difference, a y or vertical measure. And then at the bottom we could say all of that energy that was potential will go into the motion of it. So the maximum velocity happens here, and our velocity up here is 0, like that. And they are mentioned on this slide. You can see the 0 here, because these are related. And vice versa, this is your max here. Sorry, this is being slow. And then the h here, h min, if you will be like that. So, going back to this, that's just a quick energy recap of a pendulum. And same idea here, this is our equilibrium position. Now remember, we have the most amount of energy when we have the most change in height. So, if you notice that this gray curve right here is maximum right here, that's because you have the most displacement. You have the biggest height difference right here. And then if you look at the kinetic energy, notice that you get a max right at the equilibrium position. This is right at the bottom of the pendulum. And we kind of mentioned already that the maximum velocity happens at the bottom. So you'll see that the maximum kinetic energy also happens at the bottom, where this equilibrium position resides. So when it comes to finding this h, remember that we can do that technique I used in conservation of energy to find that by basically taking the length and subtracting this part right here. So we did that calculation using trig to figure out h if they don't give us to us. And I'll do an example of that. So things that affect the period of the pendulum are the following. So remember, this 2 pi kind of represents the cycle. So when you go 2 pi, that's one complete cycle. And then this represents the length of the pendulum, and this represents the acceleration due to gravity. So some of the interesting things about this is that the period is independent of mass. So it actually doesn't it doesn't actually affect our system. So that means that if I were to swing in a swing, and say you were on a swing as well, next to me, we would actually oscillate with the same period as long as we kept the same length and, acceleration due to gravity. So most swing sets do this if you have 2 swings, which is why 2 people can actually swing together in perfect harmony, if you will. So let's quickly test this out. So let's go back here. So I have a pendulum lab like this. And what you can see is I'll change here we go, let's do about 11 degrees like that. And let's do the photo gate timer to measure the period. So this will measure our period. Now they measure from the center here, but notice that this is essentially, you know, one period from this measure. So we get 2.84 from this. So let's change the mass, right? So let's pause this and change the mass to something really big and about the same angle like that. So let's play this. 2.84, remember that number? 2.84. And quite frankly, we can actually just do this and we'll see that it's still measured the same period. So the mass doesn't change it. But what will is the length. So let's make this period, make this very small up here and measure the period. So we get 1.9. So it's smaller. Now notice this is a shorter length, so in order for it to oscillate, it's not going to take as long to go back and forth. So yes, the lower the length, the smaller the period. And vice versa. If we have a big long pendulum, let's change the length to the extreme, it has to cover way more distance. So with that said, it's going to be way longer to make a full cycle. 3.18. So longer length makes a longer pendulum. Period, that is. Now the other thing was the acceleration due to gravity. So let's pause this for a quick second. So here's the Earth. So I'm just going to play with some of these just so you can see. Now the moon's smaller, so it has a smaller g. So watch what happens. Look how much it changes. Well, g is the bottom of our equation, if you could see right there. So if this number gets small, then the period gets very large. And that's exactly what we're seeing here. A very large period. Now if we do the inverse, so let's change this to planet, here's planet Earth again just to give you a perspective. You can see it sped up. So Jupiter, notice it goes faster. That's because we have a smaller number. G is smaller, which makes period. G is larger because on Jupiter G is 27, so that makes the T smaller. So as you can see, it's quicker when we look at that. Oops, let's go back here. And then if you have no G, watch what happens. It's pretty fun. Well, that's an interesting, scenario here, but when you have no gravitation to pull it back down, then what you get is constant motion due to Newton's first law. But since we have a string here, it will remain going in an infinite, go in a circle for all eternity, basically. So without gravity, this thing will just keep its motion. So that's what we're seeing here. So these are the things that affect our period. The length and the acceleration due to gravity. Because the gravity is what's pulling it down, and the length tells us how far it goes. The longer it has to go, the longer the period. So in the next videos, I'll do 2 sample problems so you can see how we can use this equation.